Hello, everybody. So for this week nuclear seminar, we are having Yannick Meurice from the University of Iowa, and he's going to speak about quantum simulation of lattice gauge theory with the Rydberg atoms. As usual, if you have questions, you can interrupt you if it's okay for you, and
Yeah, perfect.
We'll leave longer questions for the end of the discussion.
Okay, thank you very much. I will briefly introduce motivation for quantum computing in general, and then I will discuss the simplest model that you can quantum simulate, and it's a model basically that is based on the qubits, and it's the quantumizing model. And I will discuss the general idea of using noisy intermediate scale quantum hardware, so NISQ hardware. Then I will introduce a general technique that I call tensor lattice field theory that is very suitable to do simulation. And this method is also behind the discussion of lambda phi 4 that I was also possibly presenting. Then I will discuss the question of symmetry breaking and truncation in these formulations. So this formulation has, in general, when you have continuous field, you have an infinitely many modes and you need to truncate. And I will show that it doesn't break the symmetry. And then I will introduce the compact abelian model, which is a scalar QED. And it's a just compact field. So the X field is actually not there. It's just the Goldstone mode that is coupled to the gauge field. They are both compact. So that's what I call the compact abelian model. And so it has the feature of QCD in the sense that you have matter field and the gauge field. And then I will explain implementation with Rydberg atoms. And at the end, I will say a few words about the other talk I was thinking about. So the lattice gauge theory has been extraordinarily successful to deal with QCD. It's not always appreciated, but so there's something that was carefully planned and carried on bit by bit. And so we are at the point where we need to use electromagnetic correction, isospin breaking. But this is for static properties. So you can measure mass, form factor, coupling constant using QCD, lattice QCD formulated at Euclidean time. And so the Euclidean time gives you a probability distribution, and you can do important sampling. And nobody really understands why it works so well, but it does. And so that has been a major success of high energy physics in the last 40 years. Now, if you want to address the question of real-time evolution, this method don't work because you have if you're real-time, the weight is e to the is, and so it oscillates, and so you need to find something else. And so the something else could be to use quantum computer, so either a simulator that where the real time is basically the system time, or use a universal quantum computer where you can program the evolution with the Trotter approximation. And now we cannot start with QCD, and people who did not start at lattice gauge theory didn't start with QCD. So there is a kind of a roadmap, and so we go through a certain number of models that have an increasing dimensionality and symmetry. and I call this the Kogut sequence. And also, I think it's very exciting that there are a lot of devices that are being built, and it's changed rapidly, and so I think it's very exciting to try to use what is available, and in particular the Rydberg atoms are online as I speak, and soon you should be able to do your own experiment without relying on the patience or the absence of patience of somebody else. So, so the long-term physics plan is to do ab initio jet physics. So if you look at most of the collider experiment with strongly interacting particle in the final state, you will find a comparison between the data. So this is just a CMS random plot involving two B mesons in the final state. And so you compare the data with something you get with an event generator. And this event generator, so I think the most popular is a PITIA, rely on the sequence of evolution. Some use partons and are reliable, but at some point you need to get the color singlet to become hadrons, and at that point you use empirical models that are not ab initio. But so the long-term plan would be to replace these empirical model by something that sets Hilbert space with parton and evolve them according to the QCD Hamiltonian. And so that is the long-term plan. So Mike Croyd started lattice gauge theory on HP calculator. Actually, he started on a pocket calculator, and then he moved on this desktop. And so he started with a Z2 gauge theory on the 3 to the 4 lattice. And then rapidly the lattice gauge community has been carried up by the progress of the technology. And so I hope that the same thing will happen for quantum computing. So the simplest system that you can dream of is the Ising model. So it's classically it's a spin system where the spin can be up or down, and you can also look at Hamiltonian formalism by using a transfer matrix, and so the result is to have a transverse field. And so I took a basis where the transverse field is diagonal, and then you have a hopping between the sides. And so this is actually this can be solved exactly, but you can also implement it on the quantum computer using a Trotter approximation. So you exponentiate this part and then that part, and you make an error of order delta t squared. And so these terms here are local, so they are what we call rotation in the z direction. And then these sigma x, sigma x are created on the universal quantum computer with a CNOT gate. So CNOT, you have a control qubit here, and when the control is in 0, you do nothing. When the control is in 1, you flip the spin there. So these are CNOT. And you have to sandwich the X rotation between two CNOT. So it's a rather expensive process on the IBM quantum computer, but so when we started on 4-qubit, it was not very good, but more recently, given the progress they made, it became possible. If you use trapped ion, then these gates are native, so you can just use the sigma x, sigma x. They are native in the trapped ion. So that's a very simple model. Now you can program this very easily on IBM. And so if has anybody used Qiskit in this room? So it's something very easy to use. And so when we have undergraduate students, they learn these things very quickly. And so programming this circuit is something extremely easy. So it's a universal programming. So all these elements just a single line instruction. So it's very simple. And then at the end, you can make measurement, and so you will get an histogram. So in this case, gives you all the final state that we observed in this experiment. And so there's a parity preservation, so there's only 8 states that accessible. And so I also believe that for the pedagogy of quantum mechanics, doing Gedank experiment, like you take a Stern Gerlach and then you rotate it, is something that could be done concretely and would help students to get a better idea how quantum mechanics works, which is something very strange. And so using a quantum computer maybe helping students to learn how quantum mechanics works. So yeah, so we started a few years ago doing this, and so we compare, for instance, this is an experiment where you start with a qubit in the 1 and then the 3 other in the 0, and then you measure the probability for this 4 qubit to be in the 1. And so it's when you start, it's 0, then it increases, and then it fluctuates. The exact diagonalization gives you this dotted line. The Trotter approximation gives you the black line, so it's not exact. And then these are simulated Qiskit with some noise and some Qiskit that we made ourselves. And so you see that as time goes by, the difference with the Trotter, which is the best that you can expect, get worse and worse. And so there are some tricks to partially get rid of this. And for instance, you can do mitigation. So you can so these are C0 gate. If you put 2 of them, you get the identity. So you can replace this C0 gate by 3 C0 gates, and you will get a noisier result. And then so you can add 2, 4, 6, 8 gates and then extrapolate to 0 noise. So that's mitigation. And by using this method, so
you have to add more gates in order to reduce the noise?
Increase the noise. So the result is here. So when you increase the gates, you get more noisy, so you get farther away from what, and then you go back.
Okay.
Yeah. So it's getting worse to try to get extrapolation to 0 noise. So that's and so. We were able to do a phase shift measurement on a 4-side lattice. So by preparing a rough wave packet and then looking at the edge of the wave packet with and without interaction. And so the interaction creates a time delay. And so we were able to measure the time delay and estimate the phase shift. So it's a very rough calculation. It's a very simple system, but so this is something we can improve. We are working with 8 qubits. We are working with 2 flavors, and so this is just the beginning of a long story. So now, this is the Ising model, which is completely discrete. But now, if you want to do other type of field theory, so if you take the lattice model, they are defined by path integral, and you also have to discretize the field integration. And so the method that I advocate is the tensor reformulation. And so what you do is you take the lattice model defined by a Boltzmann with a Boltzmann weight, and you expand the Boltzmann weight in character. So for if you have a U1 field, or if you have a field on a circle, you can expand with Fourier series. And so the Fourier modes are discrete, so you have something that you can put on a quantum computer. And so the difficult integral are done exactly. And what you are left are Kronecker delta function that encode the symmetry. So I will explain this later. And so when you have continuous field variable, you have infinitely many modes, and so you have to truncate. And result that I found is that the truncation do not break the symmetries. And then the formalism goes smoothly between the Lagrangian and the Hamiltonian. So it's I find it very nice. And so we have written a review of modern physics, and I've written a book that I strongly recommend to everybody. And so we follow basically the Kogut sequence, starting with the Ising model, the O2 model, O3, and then going to higher dimensions. So this is pretty much following the same roadmap. And now this is a very so the tensor is tensor formulation is a very interdisciplinary effort, and so there are people from the INT here that and so, for instance, we will have an INT workshop on tensor in April next year. And so when I gave the seminar at Riverside, we started this type of workshop at the INT with Sean Wenside and Robert Perry and Mike Burrs. And so so the INT has played an important role in the development of this interdisciplinary idea. So now I will focus on a simple model, which is the O2 sigma model on the lattice. So the partition function is very simple. So you have a lattice with a side x, and then it's a cubic or square or hypercubic. So the sides are connected by unit vector, which are orthogonal vector. And so the Boltzmann weight is the cosine of the difference of neighboring sides. And then you can expand this in a Fourier modes, and the coefficients are Bessel function, and they are well known. And if you had another model, you can calculate it numerically. But the result after when you integrate, you will get Kronecker delta function. So the integration over the phi becomes trivial, but now you have weight that depends on the n that are attached to the link. So you move from variable on the sides, like in the, so this, you can think of this as space and this as time. And so you have the path integral is given in terms of these fields at the space-time lattice, and you replace the integral over this field by a sum over indices that are now on the links. And so from the point of view of doing coarse graining or renormalization group, it's very nice because you can separate the degrees of freedom that are integrated from those who are kept to communicate with larger block. So it's a now the is there a clock? So in the no, there's no clock. No, because I don't.
You keep your phone.
Yeah, or I can. Yeah, I can see it. I can see it on your. Okay. Okay. So the compact abelian Higgs model is just a gauge version of the O2 model, and so you replace the gradient by a covariant gradient, and then you add a plaquette term, and so it's pretty simple. And so now this has the usual transformation that compensates the transformation in the gradient, and is local. And now when you do the Fourier expansion, like I explained for the O2 model, so you will get something that is like the O2 selection rule. So you have the n, so these n's are attached to the links, and these n are attached to the plaquette. And so this is a discrete version of the Maxwell equation with source. And so when you have the Maxwell equation with source and you take the gradient, you get a conserved current, conserved neutral current. And so this integration is somehow unnecessary. And so that corresponds to the fact that you can pick the unitary gauge for that model. But so the process is completely gauge invariant. And so now, so when you take the limit where you can decouple the matter field by taking this to 0, then you have a pure gauge, and then these terms disappear. And so you get discrete Maxwell equation. So the E's correspond to space-time plaquette. So this is a plaquette which has one edge in the time direction, and the other ones are in the space. So you get the Gauss law. So the divergence of E is 0, and you get the other inhomogeneous Maxwell equation that relates the time derivative of the electric field to the curve of the magnetic field. On the other hand, you don't have the homogeneous one, so you have configuration that violate div B equals 0, because you have magnetic monopoles and things like this. So and so you can represent this on with a graphical method. So you have the gauge quantum number attached to the plaquette, and the matter quantum number are attached to the links, and then you have some Gauss law that relate now the difference of the plaquette to the charge or the currents. And you can do that in any dimension. So you can, so these are, time is in this direction and space in this or that direction. So you have.
I got a little bit lost here.
Yeah.
So your matter fields are living on the links now?
Yeah.
And how did this happen?
So the ends are on the plaquette, and then so this is a d mu f mu nu, and then these are the degrees of freedom on the links. And so when you give the plaquette quantum number, they completely fix the matter quantum numbers. So they leave there in a way that is completely dictated by the gauge degrees of freedom, which make this model very easy to simulate. And so you can think of the dots E as carrying charge or currents, matter charge or matter currents, but they are so you see you have two magnetic, two electric quantum number and two magnetic quantum number, and then so you have the Maxwell equation. Rho B is d dt plus J, and so the J are currents like this. And they when you give me these four, I know what is J. Is that clear?
I see. So it's not the M's, because M's
The
live on
M's are here. Yeah, and these are the ends are here. Yeah, thanks. People always complain about this slide. And so you can construct the transfer matrix in the electric basis. So this is in the 2+1 dimension. So the Hilbert space is electric, so it's associated with the space-time plaquette. So this is EX, and then you have EY. And the blue tensor tells you what the charge are here. And then you have, so it's a lasagna basically. So you have an electric layer, or you can take the square root of the electric layer, because it's diagonal. And then you put the magnetic layer, so you have the magnetic quantum number, and then you have the second Maxwell equation, and then you can build your transfer matrix, and you can take the continuum limit, and so it's explained in the detail in that paper. Now some general philosophy. So the tensor are new computational building block. So we can rewrite all the lattice partition function as a trace of a product of tensor. So these are the new. So in the old formulation, you have the actions. So the action gives you the possible theory here. Instead of an action, and so an action is complicated because it has all kind of terms, but a tensor is an algebraic object with indices. And now you can also, instead of calculate partition function, you can calculate average. So you can insert observable as impure tensor. So you do the integration with the observable, you get an impure tensor. Tensors are local. So the reason particle physics developed so nicely is because we believed in the local gauge theory with local symmetry, and we imposed renormalizability. And so this locality restricted very much the interaction that you can have with this constraint. And so tensors are local objects, and they contain all the information about the model in symmetry, and they can be coarse-grained nicely. I will not explain this. And they also connect very well to the construction of a quantum circuit. So this is why I like tensor. You can reformulate Noether's theorem in a way that is very general and applies not only to continuous symmetries, but to any kind of symmetry. And so the basic principle is that you have redundancy in the selection rules, and they are in correspondence with irrelevant integration. And when you have an irrelevant integration, you can make some gauge fixing. So if you have a global symmetry, you can gauge fix one of the variable. If you have local symmetry, then you have much more freedom, but you can see that the Noether's theorem applies something discrete, and it applies for any type of global, local, continuous, and discrete, at least abelian symmetries. The truncation, so when we did the O2 model, we had infinitely many modes. And so if you want to put this on a quantum computer, you need to truncate, and the truncation preserves the symmetries, because the symmetries are encoded in these Kronecker delta function, not in the particular value of the Bessel function. So if you set some small value Bessel function to 0, you don't break the symmetry. And it also works for like O3 symmetry, and it's actually very related to the Wigner-Eckart. So you have to keep all the, so if you do a truncation in Lm, you have to keep all the m that correspond to a given L. But if you do that, then you are also safe. And so the main thing that we learn is that by truncating, we preserve the symmetry, so we get a simplified model that has the symmetries of the original model. And so in a universal sense, we hope that this truncation has the same continuous physics than the original. There is, however, something funny that can happen when you truncate too much, is that you can get more symmetry. And so, for instance, by using the spin one, so 3 states truncation of the O2 model, instead of getting a Kosterlitz or Berezinski-Kosterlitz 2-less transition, you have a West-Zumino model with a SU2 symmetry. And so this is an example where, in fact, you get more symmetry than you expect. So now I want to get into the Hamiltonian formulation. So I show you this lasagna. So you can take a limit where the time scale becomes very small, and you can identify an Hamiltonian, and I will be staying in 1 + 1 dimension. So this is the E square term. So the E is discrete, so but it's the electric field energy. This is the gradient of the electric field, so it's the charge. So that's the matter energy. So and then you have the Rabi term that can move up and down in the electric field quantum number. So that's the quantum version of things that have a classical meaning. And so, for instance, trying to do physics with this. So this is an example where you put an electric field here, where you put 1 and then 0 E, so that's just an electric field. Now, from Gauss law, you know that there will be a antiparticle here and a particle here. When x is 0, nothing changes. So it's there's nothing you can say, but when you start turning on the x, then the electric field can spread. And so as you increase x, the spread gets faster and faster. This is a 5-side calculation that I did with exact diagonalization. And now Kenny, our postdoc, has been doing much larger simulation and got more structure, but so that gives you an idea of the type of physics that you can get with this model. And so with Johannes Zeyer, who is an experimentalist in Emmanuel Bloch and also Shanwen Tsai, Xin Zhang, Judah, and Mutyoki, Alexei Bazarov, we had a proposal for realizing this model on the optical lattice. And so the optical lattice has one direction, which is the spin. And so this is a spin 2. So this is m equals 0, m equals 1, m equals 2. So the atom can tunnel in that direction, but not in this direction. And to reproduce the nearest neighbor interaction, Rydberg dressed interaction can be generated, and you can look the details into that paper. And so the difficult part is how to get these nearest neighbor, but so that was engineered by Johannes Zeyer. Now, these experiments are very long and costly, but more recently, we were able to get Rydberg arrays. And so this is an experiment made by Alex Kissling, who was a student of Misha Luking, and is now the CEO of QuLAT, the company that offers these things online. So you have a very simple Hamiltonian for Rydberg atoms. So it's basically like a qubit. So you have the Rydberg, so you have the ground state and the Rydberg state, and so you have a Rabi term here. You have a detuning that is like a chemical potential, and then you have the 1/R6 interaction. So when you put them close to each other, you get some kind of blockade. And so this is an example of what you get if you ramp up the, so there is, so you can ramp up through the phase transition at a fast rate or a slow rate. And so the Keeble-Zurich mechanism predicts the density of defects, and so that was one of the first experiments that was done with this setup. And then I proposed a way to adapt the idea of the Rydberg dressed atom with Rydberg arrays, and so this was published last year. And so the idea is to so use this Hamiltonian to simulate the abelian Higgs model. And so there are two ways to do it. So this can be m equals 0, so you have a ground and a ground. So this is a ladder. You have two legs on the ladder. So when the top atom is in the Rydberg atom, this is m equals 1. When the bottom atom is in the Rydberg state, it is m equals -1. And when none of them are in the Rydberg state, so two ground state, you have m equals 0. So this provides a natural way to split so it provides like an L square term. And the Rydberg is a high energy term that does not shower in the too much and at low energy, and so you have transition to these states. If they are not close enough, you can have a leak. But so this is the calculation done by exact diagonalization for the abelian Higgs model, and this is done with the simulator. So I picked some value of delta omega and the distance between the between the atoms to get B zero. And so there is an excellent matching for, so this is just the matching the these 4 states with 1 state that is blocked to the spin 1 of the Abelianist model, and so you can map the interaction of one onto the other in a very simple way. This is a 3 leg model. So you have n equal 1, n equal 0, and n equal -1. At that time, the detuning had to be uniform, so I could not push this down, but now they have a detuning that can be managed locally, not in a time dependent, but you can fix the ratio of the detuning that are like local chemical potential. And for a certain range of parameter, you can get an excellent agreement without having a local detuning. And then I also did the 2 sides with the 2 atoms and 2 sides with 3 atoms. And so you can compare the simulator. And so the simulator means a classical calculation of the simulator. And the continuous line is the target model. So the agreement is not perfect, but it's not too bad. Now, if I add, but none, I was giving this story, I would have shown you a clearer picture. But so now the question of exact matching is something that should be considered in a broad context. So what we are ultimately interested in is the continuum limit of the lattice model, and the continuum limit as universal feature. And so I think the first thing to do is rather to study the simulator and then see what kind of continuum limit you can define. And some will be by design close to the target, but you can also study other continuum limits. So that's my philosophy. And so we have access to QuEra, and so there is a range of value for the Rabi frequency. So the Rabi frequency is basically the X term, so that flips the electric field. The detuning is the term that will split the m equals 0 and the m equals plus or minus 1. And so there is a range of value for these experimental parameter. And then the lattice spacing can be tuned, so you can really take the tweezer and put the atoms there, and then the interface will do that for you. So they have to be larger than 3 micrometer, and the runtime have to be less than 4 microseconds. And so no, these are the project that we are doing now. So you can first study the 2 atom system and put them far away, so they are independent. So you would just get the 2 atom system with better statistics, and then you can push them closer together and then observe the non-trivial behavior. So that's the plan. These are real picture. So this is something that Sergio Contu did at QuEra, and So this is with lattice spacing that is 1 Rydberg radius, defined as the distance where the Rydberg interaction is equal to the Rabi frequency, and this is with a closer, so the 3 times, so you have 3 atoms in a the Rydberg radius is 3 in lattice spacing. So these are things that can be done experimentally. This is my dream. There's an elevator at the University of Chicago. But so that is what is in your future. And so AWS, as at least for me and a few people, a QuLAT line, so you can click there, and then you can run Jupyter Notebook that allow you to locate atoms wherever you want. So you and then you can decide the time profile for the omega and the delta, and then it will give you histogram. So these are qubits basically. So they are labeled from 0 to 5, and then the statistics. So they take picture. So for instance, they see 306 in the ground, and then they see 28 with the last one in the Rydberg, and so you can do this with 1,000 shots. You can repeat the experiment at your leisure if you have credit, or if you have a grant that can pay for it. But so, and now the 2-leg ladder has been studied for fragmentation by Kenny Eitritter. So he has done, this is with a 10-side ladder. So this is the electric field propagating, and this is the, so when you have an electric field, you have a negative charge here and a positive charge here, and this is the charge picture. So you have positive charge moving to the left and a negative charge moving to the right. So this is fragmentation picture obtained with this 2-leg ladder in a regime where it is not obviously connected to the abelian Higgs model. And so the phase diagram for the single line as Z2, Z3, and Z4 ordered as you get the, so this is the distance as the inverse distance between the atoms increase. So when you get them closer and closer, then you get these periodic configuration. So if you have, when the lattice spacing is 1/2 of the Rydberg radius, so when R over A is 2, then you have a Z2 order. When it's 3, you have a Z3 order, and so on. So this is the one leg. So it's not a ladder, one line of Rydberg atoms. And so we are currently investigating this region with the 2-leg ladder. And Jin Zhang is finding something very nice, and I can speak a little bit privately over this, but it's not published, so I don't want to show the preliminary result. So we also have tried to realize these complicated phase diagram by putting a perturbation in the O2 model. So you can put a cos q phi, which in general lose the 2 pi periodicity. When q is integer, you keep a zq symmetry, but otherwise you break the symmetry. So we first look at this in the limit of large gamma. And so you have the clock models here at q. So this is a Ising Z3, Z4, Z5, Z6. And then you have Z2 region where, so when the clock has one more state, you have two states that are nearby. And so this is kind of an Ising model. So we get this phase diagram. So now the question is what happens when you reduce gamma, and the resemblance with the Rydberg atom is kind of compelling. However, the lobes here are not floating phase or BKT transition, they are just crossover. So I think we need to put one more parameter to get the configurable array phase diagram. Okay, so now that's the end of the first talk. So the talk I was thinking to give today is about 5.4. So 5.4 is a continuous version of the Ising model, if you want. It's in the same class of universality. And so you can, when you take lambda large and you have a negative quadratic term, you can have a deep potential with two minima. So it's connected to the Ising model. Now, so this is the standard model that people study in the field theory class, because the Feynman diagram are very the most easy to calculate. And so if you have done this calculation, you know that the series don't converge for any, no matter how small lambda is, the series is divergent. And so the reason is very simple. If lambda was negative, then you get unstable potential, and so you can produce particles, and they will go to the bottom of this inverted potential, and so there is no stable vacuum. So if you had a finite radius of convergence, it would give meaning to this meaningless situation. And so that's something that was pointed out by Dyson. Now, when you digitize this model, you keep only a finite number of value for phi, and it kills this argument. So there's a minimal energy that you can reach by going to the end of the negative 5.4 potential. And so perturbation theory is convergent. And now the question is, so one of the motivations to do quantum computing is that you cannot use Dyson series for 5.4 to calculate the real-time evolution. So this is to do real-time evolution. So standard method, so Dyson, or you can also use the spectral decomposition and then use a time-independent perturbation theory, and you can also obtain the evolution of the rate. And that is a better method that we have discussed there. Now, so this is an illustration of the singularities of the perturbative series.
Sorry, Yannick, we're running out of time.
Ah.
Can you give us a short version?
Yeah. So there is a finite radius of convergence, and you can do analytical continuation. And so you can do perturbation theory. Now you can look at the paper, and if you want to get in this region, and you can also use trunk coupling, but if you get an intermediate region, it's probably very costly. So it is there's probably a quantum advantage if you want to work there. But if you want to work here, you can use perturbation theory. Yeah. And you can validate your quantum computation by using perturbation theory. We also have done quantum simulation of the end flavor Gross-Neveu model. And so just to conclude, so this is the group, quantum group at the University of Iowa. So and the person that has done the perturbative calculation is Robert Maxton, and the person who has done the calculation for the phase diagram is Jin Zhang, and the Kenny Iterator has done the fragmentation model. And I'm also part of the QuLAT collaboration that includes NSU, UCSB, BU, Syracuse, and the University of Maryland. And that has been a great source of inspiration for me. And so I'm exactly at the end, and so you can read the conclusion. So
Thank you. Any questions?
In these real-time problems, you also wanted to at the same time understand some finite temperature. Is that possible to model the circuits, or is it?
To do finite temperature, you need to insert the e to the minus beta h, which is non-unitary, but so there are people who have been working on this at Fermilab, for instance. Erik Gustafsson has been looking at finite temperature effects. So yes, it's possible.
How do you prepare the packets? And how do you measure?
Yeah. So to do scattering, you need a wave packet. You need or two wave packets. So the general idea is to prepare the ground state. And so there are several methods. One is to use a variational method. The other is to use MPS, so a one metric produce state solution, and you can implement it side by side on a quantum computer. I don't think it has ever been done in practice. And then when you have the ground state, you have to create a particle excitation, and then you have to make it Fourier mode. So you have to create Fourier modes for the particle. So it is the most costly part of the program. The evolution is something very local, so that's easy. And then the measurement at the end is also Fourier transform, which is also expensive. So these are.
How do you measure the? Oh, you said you measure the Fourier modes, therefore you can measure the temporal length.
Yeah. So what I did is with other people is to look at the reflection probability. Let's see if I can. So this So this is the probability to be in the reflected mode divided by the sum of the inside and outside mode. And so when you get 1R, it means that it's basically the rebounding on the wall. So it's a 50-50. And so this time is very characteristic. So when you put an interaction, it creates a time delay. And so the edge of this wave packet will move to the left. And so to do that, we had to do Fourier analysis of the final state, which is expensive. Yeah.
Question on Zoom?
Is there any question from this Zoom audience?
Yes, I have a question. Hi, Yannick. This is James Very.
Hi.
Hi, how you doing? Thanks for a wonderful presentation. Very, very interesting approaches that you're outlining and presenting results for. We have some interest locally at Iowa State in the problem of solving for the critical coupling of phi to the fourth. And we've spent some time looking at this in light front formulation. I wondered if you had given any thought to trying to solve for the critical coupling.
Yeah. So I was going to give another talk where I discussed the critical coupling, but the audience had more interest in the Rydberg atom. But I can. So first, this other talk, I came here 21 years ago and I had a very nice discussion with you, and then I wrote this physical review letter. So I wanted to thank you for helping me with this, finding out that the cutoff in the field gives you a convergent perturbation theory. And then we have done calculation that I didn't show today with the digitized version of so can I show it? Is it okay to so now
Yes, please. Yeah.
So let's see. So we have done calculate, so that we looked at phi-4 in the Hamiltonian formalism. So the model is here. So we have an harmonic oscillator with a just a hopping term, and then. So we have looked at the singularities of the spectrum for 4 sides. And so the results here. So this is so where does he see me? If I look there, yeah. So this is the coupling constant, and this is a very small hopping. So these are just a collection of single harmonic oscillators. So the singularity is basically where the singularity of the single oscillator is, and it's negative coupling with an imaginary part that controls the width here. So this is not a transition. Now, when you increase the hopping, so the hopping is something that will drive you in the ordered phase, and so if it is large enough, you will get in the critical. Region. So when I increase the hopping, I get singularity with a very small imaginary part and a positive lambda. And so this lambda is close to the critical the critical volume. So this is the imaginary part of the critical of the singularity, and so it decreases, so it gets closer and closer to the real axis, and now the real part becomes more and more positive, so there is probably a transition. But so this is a very crude calculation with 4 sides. And so this is just by exact diagonalization. And so you can do perturbation theory as long as lambda is below point, it's kind of small, below 0.02 or 0.03. But so you can see the critical volume developing in this 1+1 dimensional mode.
Then the continuum limit would be what? Taking NS large?
So it depends what you want to do exactly. So it has a second order phase transition. So you can approach the critical point from the left or from the right, depending if you want to be in the ordered phase or the disordered. So you have to approach the region where the perturbation theory is stopped converging.
So to compare this with other results in the literature, you would have to go increase NS. Is that the right way to say it? Number of sites?
Right. Yeah.
Yeah. Okay. Okay. Very interesting. Thank you. Thank you.
Yeah. Thanks. And so there's a preprint with this. So if you want to see it came 2 or 3 weeks ago. So,
I think that's all. Okay. Thanks, Yannick, again. Almost 2 o'clock.
Thank you very much.
Thank you.
Thank you very much, Johnny.
Thanks.
Bye.
Bye-bye.